Input signal mode of op-amps. How connect the inputs to the op-amp. So it has different modes of inputs in the op-amp. The first one, single-ended mode. Single-ended input operation results when the input signal is connected to one input with the other input connected to the ground. Let's see in this feature, our input is in non-inverting input voltage. Non-inverting. So in the output, in phase, but amplify the signal. It's large, our signal becomes large, but in phase, with the same phase with the inputs. But in this feature, when you see our inputs are in the negative signal, that means inverting input voltages. So in the output, they inverted. This is positive, but in the output, inverted. So this method of input mode, we call it single-ended mode. So when you in non-inverting is using, the other input becomes grounded. The other input becomes grounded. So in phase A, the inputs applied to the plus input with minus input to the ground, which results in an output having the same polarity as the applied input signals. In figure B, shows an input signal applied to the minus input, the output then being opposite in the phase to the applied, that is inverted in the output. The second one, differential input mode. In addition to using only one input, it is possible to apply signal at each input, this being a double-ended operation. When at the same time, when given an input signal to inverting signal and also non-inverting signals. When two opposite polarities out of phase signal are applied to the input, this type of operation is also known as double-ended or differential input mode. So in this feature, above shows the same action resulting when two separate signals are applied to the input. Therefore, the amplified difference between the two inputs, V1 minus of V2. So V difference appears on the output. So that means what I tell you in the first, when inverting is greater than this non-inverting, the output becomes inverting output. When non-inverting is greater than this inverting, the output is non-inverting in phase. The third one, type of input mode, common mode. When two signal voltage of the same phase frequency and amplitude are applied to the two inputs as shown below, both are the same polarity, positive. Common mode operation. When equal input signal are applied to both inputs, they cancel, resulting in zero output voltage. That means ideally the two inputs are equally amplified, and since they result in opposite polarity signals as the output, the signal cancel, resulting 0 volt output. This action, common mode rejection ratio. So its importance lies in the situation where unwanted signals appears commonly on both op-amps inputs. That means the signals which are opposite as the inputs are highly amplified, while those which are common to the two inputs are only slightly amplified. The overall operating being to amplify the different signal while rejecting the common signal as the two inputs. Since noise, any unwanted input signal, is generally common to both inputs, the differential connection tends to provide attenuation of this unwanted input while providing an amplified output of the different signal applied to the input. So in the common mode input signal, there is unwanted input signals, so it's rejected by common mode rejection ratio. Ideally, an op-amp provides a very high gain for desired signal, single-ended or differential, and zero gain for common mode signals. But practically, op-amp, however, do exhibit a very small common mode gain, usually much less than 1, while providing a high open loop voltage gain, usually several thousands. The higher the open loop gain with respect to the common mode gain, the better the performance of op-amp in terms of rejection of common mode signal. Therefore, good measure of op-amp performance in rejecting unwanted common mode signal is the ratio of open loop voltage gain to the common mode gain. This ratio is called common mode rejection ratio. So this common mode rejection is one parameter of op-amp. So CMRR becomes open loop gain over common mode gain. The higher CMRR is better. Also, unwanted signals is measured in decibel. So CMR often expressed in decibel as CMR 20 log open loop gain over common mode gain. Let's see examples with examples, but how they operate in differential mode, in common mode, or how to calculate it. When separate inputs are applied to the op-amp, the resulting difference signal is the difference between the two inputs. So V differential becomes V input 1 minus V input 2. So that means maybe V non-inverting minus of V inverse. That is V differential. So differential amplifier, so far in conventional amplifier, we are assuming single input and amplifier output as the output terminal. However, we can design an amplifier circuit that accepts two input signal and amplifies the difference between the two signals. Such amplifier is called differential amplifier. Look in this circuit, 25.2. Our input is single. In this feature shows the block diagram of an ordinary amplifier. The input voltage is amplified to gain of the voltage, where A is the voltage gain of amplifier. Therefore, the out voltage is V out. So V out becomes gain multiplied by the V in. But in the second feature, feature 25.0, as shown, it has two inputs in the op-amp. Shows the block diagram of differential amplifiers. There are two input voltage, V1 and V2. This amplifier amplifies the difference between the two input voltage. Therefore, the output voltage is V out becomes gain of V difference, V1 minus V2. So, what we do in the conventional type of amplifier. So, in common inputs, how they operate, when both input signals are the same, a common signal element due to the two inputs can be defined as the average of the sum of the two signals. So during common mode, how to calculate it, V common becomes 1 over 2 multiplied of V1 plus V2. So the average of input voltage. So for both common inputs and differential inputs, how to get the output voltage. Since any signal applied to an op-amp in general have both in phase and out of phase components, the resulting out can be expressed V out gain of differential multiplied by voltage differential plus gain of the common multiplied by voltage of the common. So VD difference the voltage by equation 14.1, common voltage by equation 4.2, AD differential gain of the amplifier, common mode gain of the amplifier. So let's see simple example. Look it. Calculate the common mode rejection ratio for the circuit measurement shown below. Our input in this feature, it has differential input. In non-inverting, a positive 0.5 millivolt. In an inverting input mode, input voltage, a negative 0.5 millivolt. So V difference becomes V1 minus of V2. So the given is V out becomes 8 volt. So must be determined first the gain of this op-amp. Again, in the second circuit, it has a common mode. Both are positive 1 millivolt and 1 millivolt, and our output is 12 millivolt. So V common in this 1 milli plus 1 milli over 2, that becomes 1 millivolt. So again, for this common mode must have get a common mode gain. So to calculate CMR, let's see our VD becomes V1 minus V2. So V1 0.5 milli minus of V2 minus 5 milli. This becomes 0.5, 0.5, 1 millivolt. Again, in voltage in the common mode, 1 over 2 multiplied V1 plus V2. So as you see, in common mode, our input is 1 millivolt, 1 millivolt. So 1 over 2, 1 milli plus 1 milli. So this becomes 1 over 2, 2. So 2 by 2. This becomes 1 millivolt. So to find V out becomes gain of differential multiplied V differential plus gain of the common multiplied by V common. So first find the gain of differential. So in the first circuit, that the V differential V out becomes 8 volt. So for this one, V out in differential, that gain of differential Vd. So our V out 8 volt. So 8 becomes a gain of differential. Vd becomes 1 millivolt. 1 millivolt. 1 millivolt. So gain of differential becomes 8 over 1 milli. So this becomes 8,000. Our gain of differential. The same for common. For common, V out of the common, gain of the common times common VC. This become, our common becomes 1 milli AC. VC becomes a gain, V out, sorry, our V out 12 millivolt during common mode rejection ratio. So this is 12 millivolt. So our common mode 1 millivolt. So this becomes gain of the common 12 milli over 1 milli by milli. So 12 for common mode. Then CMRR becomes gain of the difference over gain of the common. So 8,000 over 12, this result is becomes 666.7, the rejection ratio of the signal. Or you can also CMRR represented by display. So CMRR becomes 20 log AD, that is differential gain, over AC. This result becomes 56.7. So let's see the result. Look at the gain of differential 8000 from the measurement in the feature in the above what you see. The measure shown in feature 4p using procedure step 2 above for common gain again 12. So using CMR calculation, our CMR is the rejection ratio 606.7, also expressed in decibel 20 log AD over season. This becomes 56.48. So this becomes 56.8 decibel. So this is how to operate an op-amp with common mode and differential mode. So where they apply op-amps, application of op-amp, amplifier provide gain in voltage or current. Yeah, that is gain. That means the ratio of output into inputs, that we can call it a gain. So op-amp can be used to convert current to voltage. So what type of op-amp circuit is used in convert current to voltage? We will see in the latter. Again, op-amp can be used also a buffer between two circuits. Op-amp can be used to implement integrators and differentiators. Op-amp can be used also active filters, low pass and band pass filters. So we will see all these applications by using different op-amp circuits. So basic op-amp circuits, we have a golden rules for op-amp circuit analysis. The first rule, V non-inverting minus V inverting becomes 0 always. The second rule, current non-inverting equal to current inverting. This becomes also 0. So this means the voltage between both inputs of the op-amp is forced to be 0. There is no short circuit between both inputs because the current is also 0. The circuit between both inputs is called virtual short circuit. So V becomes 0, I becomes 0. Virtually, both inputs short circuit. So virtual means it seems like it is virtual, but not really. So as you know, the gain of the op-amp is so high, it reaches up to 10 raised 6, that a few microvolt as the input will swing the output over its full range. So any feedback control of Vout attempts to do whatever is necessary to make the voltage difference between the input zeros. The input impedance of op-amp is very high, so it draws very little input current, that is 0.08 microampere for 741 type of op-amp, or picoampere for FET input types. So this input current is negligible. So let's to understand what does the concept of virtual short circuit. So virtual short circuit, as you know, during open loop gain, our range is, it reaches 10 raised 6. So during op-amp inverting non-inverting input, V inverting, V non-inverting inputs, when you need to get a V out, so V out means the gain of V difference. So let's assume V out is 10 volts. So to get V difference, V out means gain of open loop gain multiplied by V difference. Now our V out is, assume 10 volt. So gain of open loop Vd. So our gain of open loop is, it reaches 10 raised 6, 10 volts becomes 10 raised 6 of Vd. Vd becomes 10 volts over 10 raised 6. So our result, Vd becomes, when 10 divided 10 raised 6, 10 microvolt. So this result is that is no voltage. That means Vd minus V inverting minus of V non-inverting minus of V inverted. This becomes 10 microvolt. So this input current is negligible. So this input voltage also negligible. So this becomes 10 as 0. So V non-inverting of V inverted becomes 0. That means V non-inverting equal to V inverting. That is a rule of op-amps. So for the next op-amp circuits, during different type of circuits, we use these rules. So this is a op-amp introduction, parameters of pump, ideal versus practical, and applications of op-amp. The next we will see op-amp circuit type or different circuit, like inverting, non-inverting, summing, differential, integrator, and differentiator. For today, that's my thank you for your attention. If you have any question, put in your comment. Thank you.